Hello.
Hello, Yusuf. So, no backstage needed for this one.
Yeah.
Okay, then I wait 1 more minute and then we start.
Okay, I think it's time. And hello, everyone, in the next series of this session. And I have Philip Reisner with me, and he is the CEO, a very technical CEO of Linbit. And he will explain everything about Linbit, LINSTOR, and DRBD in this session, and as well as your questions. So please, if you have any questions at any time during the session, during the presentation, please ask them in the chat and we will try to give you a great answers, hopefully. Okay, Philip, I might interrupt you sometimes during the presentation, maybe with the questions. But please go ahead and start your session.
Thank you, Yusuf. Okay, then let's jump in here. So let me start with a few words about the company. So Linbit is an open source company, a Linux company. So that's our DNA. That is what we do. So we founded like 20 years ago. It was in the year 2001. We have our main office in Vienna, Austria, and we have one additional office in Portland, Oregon. But in times of Corona, offices get less important. We work with partners all over the world and with customers. And we are focused on storage on Linux and storage replication on Linux. So we're doing this in a very low level way, and DRBD is one of our corner building blocks. It is an open source component. It is a component of the Linux kernel, well, an older version. And that's mainly there to replicate block storage. Then in addition to that, we have a component called LINSTOR. That is there to orchestrate DRBD and lots of other building blocks of the Linux kernel. Then there's Pacemaker to build high availability clusters. And out of these, let's call them technologies, we build the products we go to market with, and that's Linbit SDS and Linbit HA. And as you can see here, we have a number of customers all around the world. That makes Linbit possible. Now, the next 4 slides, they are like the very high altitude overview, and I will more or less fly over them only very quickly so that I can use more time on the in-depth part. So when would you use Linbit SDS? When you need persistent volumes for containers, when you need persistent volumes in virtualization, context like OpenStack, OpenNebula. For what kind of applications is it a good fit? For everything that is demanding regarding the I/O subsystem. So databases, SQL databases, message queuing systems, that's all transaction processing. It's also a good fit for analytic processing. In this area, you need high read throughput and intermediate with high write throughput. Also here, it proved to be a very good fit. Why is it so fast? Our data path is based on a kernel component. I will go into more details soon. We do volume allocation. We lay out volumes at allocation time. So this is in strong contrast to what other solutions do in that area. We build on existing components like DRBD, LVM, and so on. And it is a very good fit to be used hyperconverged because it uses very little CPU and very little memory.
That's always a question because people ask, what is the minimum CPU and memory recommendation that we need for Linbit STS? So
and yeah, the answer is, it also runs on Raspberry Pis.
Yeah.
And allows you to still run the application you would otherwise run on your Raspberry. So it is a very small fraction of CPU and a very small fraction of a single CPU core in case you have a multi-CPU system like, 64 cores. Yeah, then in regards to the size of clusters, so I would say the smallest reasonable cluster has 3 nodes, and it can manage clusters of up to thousands of nodes. It can manage multiple storage tiers. So let's say a SSD-based one and a HDD-based one. And you can have complex policies. Let's go into that later. How does it achieve the resiliency, the persistence? By replicating data. So usually you would do 2-way or maybe 3-way replication, but it also supports more. It can do this synchronous, asynchronous, and snapshot shipping. You also have ways to influence how it uses the network, which paths over the network it uses. And all that can be part of your business contingency plan. Okay, that was the high-level overview. Let's start to dig into the guts of it. So a short overview, what do we have in Linux? Because we will reuse all these building blocks. So just as a short reminder. So there's LVM, and what does it do? You take one or more physical volumes, combine them in a volume group, and out of that you can have logic volumes that might be tiny, or span multiple physical volumes, and snapshot of those. This is pretty old. I think it's about 20 years available. Then a few years later came thin provisioning to the thing. So now we take one of those logic volumes and mark it as a thin pool. And out of the thin pool, we can create thinly allocated logic volumes and snapshots of those. Here, the big advantage is that they share the exception tables. So that means we can take many snapshots and it still performs reasonable. It doesn't degrade in performance. Another building block is software on Linux. So it's also available since, I guess, 30 years, 25 years. So originally there was the Nvdimms command, and you have all the RAID levels from striping to mirroring to RAID 5, 6, 10. And nowadays it's also accessible through Device Mapper and the integration with the LVM tools. And yeah, it does what software RAID does, right? Then there is deduplication on Linux. So that's maybe a more recent addition. Currently, it's only available on the RHEL platform and the clones of RHEL. So CentOS, Arma Linux, Rocky Linux, you name it. It is there since RHEL 7.5. It's called VDO, or the long name Virtual Data Optimizer. And it is a regular block device. So usually you would use it below the LVM level. And then if you have, let's say, redundant images in your logic volumes, let's say a number of Windows VMs, then video will, find those duplicate blocks and store them only once, and a little bit of information in its metadata. Let's see how the journey goes when this finally lands in upstream. It's on GitHub right now. We have a number of implementations of caches in Linux. So here, on this slide, I only have the most prominent ones. All three of them are in upstream, and they have different, let's say, specific targets. So Bcache is like the generic one you would use if you have an NVMe drive in front of a hard disk. Similar with DM cache, but this one is integrated with device mapper. And with that, it inherits certain limitations from the stack. DM write cache, you would use that if you want to combine PMEM and NVMe drives. And above and beyond that, there are at least 6 other ones. Most of them are out of 3. So there are plenty of those solutions. We have also targets and initiators in the open source Linux world, many of them. Most relevant for the SCSI related protocols is LIO. So it does iSCSI, ISER, SRP, fiber channel, F fiber channel over Ethernet, and everything that has SCSI in it, right? And that's the implementation that ships with all the current Linux distributions. The other ones are more of historical interest right now. And there's also the new kid on the block, NVMe over Fabrics. So we have target and initiator in the upstream Linux kernel, and also available in the recent distributions like RHEL 8.2.3, something like that. And its clones, of course. And when I talk about storage components on Linux, I shouldn't leave out CFS or ZFS. So it brings its own logic volume manager that's built into it. That is also capable of doing thin provisioning. It has its own RAID implementation, and it has its multiple components in it are about caching, like the L2 arc and so on. And it also has a file system, but from my point of view, I'm mainly concerned about its logic volume management capabilities. Now let's talk about DRBD. So from a very high level point of view, DRBD is like a RAID 1 between a local packing device and a second packing device on another node. And in between, we have an initiator target combination. But it's implemented as a driver on Linux, and it gives you a block device accessible on all the nodes. And in the moment you open this block device for read-write, it promotes its role to primary. And that determines our direction of replication. If we want to move the workload to the other node, that's pretty easy. We stop the workload, we unmount the file system, we mount it at the other node, start the workload here. Then this guy would be primary, this guy would be secondary, and it would replicate in the other direction. So that's called auto promote, and that makes the process pretty easy. It does multiple volumes. So we could have volumes of very different characteristics. Let's say one is an NVMe drive. Let's say the other one is a RAID 6 of rotating media. So pretty different in terms of latency and throughput. But we could use them together. Let's say we have a database and put the table spaces on a huge device, and the write-ahead log on the fast device. Then it becomes obvious when we mirror that, we need to mirror them together. Because if the fast device would overtake the writes on the slow device, then the database would not be able to recover after a failover. So to mirror that in a consistent way, that's called a consistency group. Yeah, so that's supported in DRBD. And DRBD would allow you to have up to, I don't know, 60,000 volumes in a single consistency group. Nobody needs that. Usually it's 2. It's also not a 2-node technology. It can mirror from a single primary to multiple secondaries concurrently. And each of those replication links might be synchronous or asynchronous. And that can be switched at runtime. It also supports a diskless mode of operation. So that means we could have here 3 nodes in a DRBD setup. One of those doesn't have a local replica of the data, but it still exposes the dev DRBD device. So we can mount it and start the application. So it now acts like a iSCSI initiator that is connected to 2 targets concurrently. But it has a huge advantage. If one of those guys with disk fail, everything continues for the application. Because if we had a read request that was being processed on this node and it crashes, then this primary node will simply retry the read request down here, get the data back, and deliver it to the application. So the application is shielded from any errors as long as possible.
Yes.
Yeah. In case the node comes back, DRBD will do a resync, bring it back up to the up-to-date data, and everything will continue. And also this guy, the primary, can be configured. Well, in this setup, it will do read balancing. So for every read request it gets from the application, it will send one here, one there, one here, one there. Well, it's not as easy as that, but it basically can use the double read bandwidth, right? For writes, it needs to send them to both. So for writes, you get the single bandwidth. All of that under the assumption that your network is much faster than the backing block devices. So all this technology has been in development for about 20 years, and it got a number of bells and whistles on the way there. So like, if something fails, it figures out in which direction it needs to resync. It always does a partial resync, except if that is not possible. You can further save on bandwidth with a so-called checksum-based resync. Of course, it detects if there was a split brain situation. It has recovery policies for that. And most importantly, we want to avoid that we run into split brain at all. That is possible with fencing in the old world and with quorum in a new software-defined storage world. You can have lots of such DRBD devices per server. Thousands is possible. And it supports a so-called dual primary mode for live migrating VMs. So if you do virtualization with KVM, KVM is capable of live migrating a VM from one machine to another. But for that, it needs to open the backing block devices on a target machine before it releases them on the source of the migration. And for that purpose, it might be primary concurrently for the duration of the live migration.
So dual primary is like both machines are capable of write in the same time, and then one of them becomes secondary after live migration ends, right?
Correct. Okay, then. So what did we do recently? So recently we added support for persistent memory and Nvdimms. And support wouldn't be necessary because they appear as block devices on Linux. So DRBD worked with that out of the box. But persistent memory and Nvdimms they have an advantage over regular block devices because they allow us to access smaller units of storage than a whole disk block. And we optimize DRBD that we can take advantage of that. And with that, it's possible to get better IOPS. When you combine, let's say, NVMe drives for your regular data and just a single PMEM to put the metadata on. So we have there a nice blog post describing the benefits and the measurement results from our lab. And Windows DRBD is coming along very well. We expect like the 1.0 release within November 2021.
Before passing into the next slide, so we have 2 questions regarding to this slide. So let me ask them. The first one is from Roman. I guess it's Roman, yeah. And he's asking when to expect a DRBD 10 and the erasure coding. Is it slower when in comparison with the standard replication? And because you wrote down like we started DRBD 9.1, I think it's related. So
yeah. So we did some work on erasure coding in the course of the DRBD for Cloud project. But that is currently, let's say, demonstration code. And currently we are not moving forward with it because we are so busy with all the other things, all the other optimizations that are ongoing. So from point of view of today, erasure coding, if it ever comes to DRBD, would be at the earliest of 2023. So what we have now on the roadmap is a DRBD 9.2, and it will have latency optimizations. That's pretty interesting, where we remove one of the DRBD kernel threads and do more processing in the so-called bottom half of the kernel. So that saves CPU time by reducing the number of scheduler calls that happen in the system. So the first measurements we have are pretty impressive. So in some workloads, removing hundreds of microseconds from I/O completion times.
Interesting.
And the other thing that's ongoing behind the scenes and will be soon released as DRBD 9.2 is optimization between resync and regular I/O. And yeah, it's also very interesting for these cases where you have high performance devices like fast NVMe drives and a really demanding database, and at the same time you want to do a resync, right? Yeah.
Okay, thank you.
Then let's move on to LINSTOR. So far I was talking a lot about all these components. And all these components, so like DRBD and LVM and CFS and VDO and LUKS encryption, they fit all together. They can be combined on the data plane level, so I can stack them as I need them. But that becomes pretty complicated in management because many of those storage tools bring their own configuration utility. And this is exactly the space where LINSTOR operates. So the idea of LINSTOR is that you take a bunch of Linux nodes, and LINSTOR will configure pretty complex storage stacks for you And it will do that through a REST API. And on top of the REST API, we have now integrations, connectors to Kubernetes, to OpenNebula, OpenStack, and so on. So, oh yeah, and of course, it's open source. Right now, we do LVM, LVM Thin, CFS, and a few more. And let me go into an example to explain how this LINSTOR thing works. Or let's say the combination of DRBD and LINSTOR. So on this slide, I have a cluster of 6 machines. And it's machines that have enough CPU and memory to run the actual workload. Might be VMs, might be containers. And each machine also has built-in storage devices. So let's assume NVMe drives. And I need to add, this illustration is true no matter if it's an OpenStack, an OpenNebula installation, or a Kubernetes installation. So from our point of view, these orchestrators are pretty similar from point of view of a storage software. So we get the request for a new volume. And let's say we have a policy that says it should be two-way replicated. Then LINSTOR will try to create one replica on exactly the node where the workload will run. So here for the orange VM or for the orange container, one replica is located here. And it will allocate a second replica somewhere else. So here, and it does the same for the black one. Now this layout is special because when we execute read accesses, we can fulfill them locally. So the overhead for reads is like nearly zero. Only for writes, we need to send something over the network and wait for the acknowledgement to come back. So we create network load and we add network latency to the completion latency. But keep in mind, for reads, it's nearly free.
Yeah.
And now, what can happen to a cluster like that? It can happen that we migrate a virtual machine, right? That is possible and supported. And now this guy operates like a diskless primary, right? So now it needs to send the read requests to the other nodes. It can do that in a load balancing fashion, but still we added that. And here's the important part. Now LINSTOR supports to migrate the storage to the workload, but it doesn't have to do it, right? If your hardware setup, your cluster, if your network is so much faster than your backing devices, then you might choose, well, we never do this. We'll let it run in that way, right? But if you decide that LINSTOR should migrate it, then it looks like that. So LINSTOR will try to allocate another replica for this. Then it waits until DRBD resyncs all the data there. And after that is done, it would remove this third replica because the storage class only requires 2 replicas. Yeah.
That's great.
That's the example. Then I just discovered here a question in the chat.
Okay.
So let me jump to that question before I continue in my slide deck. The question is from Victor, and it reads, how long does it take to switch client I/O from primary to secondary or secondary to secondary? This switch time is like probably 2 times the network latency. So in essence is you need to wait until I/O is drained on the primary, then it releases the primary role and immediately after that, the other node can become the new primary. Yeah, so the answer is like in no time.
I also have some questions regarding to LINSTOR, but I think I will wait until you finish the infrastructure and then we'll move on.
Okay, then let's move on here. And let's have a look at the LINSTOR architecture.
Okay.
Yeah, so the components of LINSTOR are the LINSTOR satellite and the LINSTOR controller. Let's start with the satellite. The satellite is stateless, configurationless, but it's a daemon. So you would install the RPM or the Debian package, make sure that it is running, and that's it. And you start that on all storage nodes and on all compute nodes or on the combined nodes. In a Kubernetes cluster, it is as easy as running a stateless container. And that is done by some operator, so you don't care about it. Then the LINSTOR controller, that's the central part. So this one has state. So usually it has a built-in SQL database. But in a Kubernetes setup these days, we put the state into custom-defined resources in Kubernetes itself. So in Kubernetes context, even the controller is stateless. Well, stateless in the sense that it doesn't need a persistent volume.
Yeah.
And that's very nice because we provide persistent volumes. Would be stupid if we require a persistent volume. Okay, so the controller can move around as well. In the Kubernetes case and in the other case, it can also move around because we would put that state on a manually managed DRBD device. And yeah, the controller, since it has state, it has a database of all the nodes in the cluster. It reaches out to all the satellite instances. It establishes a TCP connection and it uses them to do all the storage configuration there. But what I want to remind you is that the LINSTOR controller is not part of the I/O path. So when a volume is established, then all the data replication, all the communication of the data path is independent of this structure. That also has another impact. The other impact is the control structure is in itself independent. So we can restart a satellite and there will no harm be done to your active volumes.
Yes.
They continue to do I/O. So you can even upgrade the whole LINSTOR structure and keep the I/O running. And this clearly separated data plane and control plane, I think that is something that sets us apart from many other solutions out there. Yeah, what else is here? We have the REST API. So it might be clear or TLS encrypted. We have the client library, the CLI. There's also GUI, and we need to add that to this graphics. And we have all these connectors.
Maybe I can squeeze a question here. So, for example, we use CSI for Kubernetes, right? And many others for the other orchestrators. So, our favorite customer, KeyWebs, asked a question. Is a pluggable interface for LINSTOR is planned, like CSI for Kubernetes, and to have an opportunity to add support for third-party backends?
Okay, yeah, very good question. So it's not yet planned, but let's say I have it on the back of my head. I understand that our current model, where all the drivers are in the upstream project, might be limiting for some players. So yes, let's put it that way. It's on the longer roadmap to have pluggable backend drivers.
Okay, thank you.
Then let's move on. And let's have a look at what is managed by LINSTOR. So of course, it manages all the nodes in the cluster. It knows them, right? Then we have something that we call resources, and that's just containers for volumes. We use these containers to express consistency groups of volumes, so storage volumes. We have snapshots of storage volumes, well, actually of resources, because we can take snapshots of multiple volumes in a single operation. There are storage pools. So a storage pool would be a LVM volume group on some node, or a CFS pool on some node, or on many nodes. It even supports shared storage pools. So what is that? That would be shared storage attached to multiple Linux machines and managed by clustered LVM, or even by a single node LVM accessing the same shared storage device. A little bit exotic, but it's supported. Yeah, and resource groups, that is the most important thing. And you know, the illustration looks a little bit like LVM, but it is a bit different, because a resource group doesn't group the storage in a physical way. It is more like an allocation policy. So in such a resource group, you define, okay, or another word for it would be a storage class in Kubernetes. So what you express in this resource group is how many replicas should virtual volumes have that are in here, on which kind of backend device should they be placed, like on hard disk or an SSD. Are there certain placement constraints, like 2 replicas need to be in the same rack, but different chassis, or different racks, and a 3rd replica in a different room? All of this goes into the resource group. And a resource group is then a one-to-one mapping to a storage class in Kubernetes, or similar concepts in the other workload orchestrators. Yeah, and out of the resource groups, we create usable volumes, like DRBD replicated volumes or persistent volumes. A plain volume would be like an ephemeral volume, so where you don't have guarantees that it survives the node failure. Or encrypted volumes, and it could also be encrypted replicated volumes, etc. Oh yeah, and the last thing I need to mention are these Aux properties. So with that, you can attach like tags to your node, to your nodes, like arbitrary labels. And you can refer to these arbitrary labels out of the allocation policy in the resource group. So this is where, well, let's say that all the powerfulness of LINSTOR lives. Yeah, then here a few words about the layer stacks. So in each resource group, such a layer stack might be placed. And the only layer that is really required is something that can allocate storage. So like a LVM volume group or a ZFS C pool. We also have some more esoteric here, like a Seagate Exos, that's a hardware appliance from Seagate. OpenFlex, that's a group of products from Western Digital. SPDK, the well-known user space, block driver, and I'm not sure, maybe there are even more these days. there might be video, there might be encryption, caching, and the NVMe target and initiator in between. And yeah, and the DRBD layer always sits on top. So the replication is always placed on top. But as indicated here, some of these layers are optional. Only this bottom layer is required.
So that means LINSTOR can run without DRBD. So you can manage your infrastructure without replication, or maybe with replication with some other way, I don't know, in the backing device. But you need to provide an LVM or a ZFS pool to use it, or maybe a direct backing disk. That's something I don't know yet. Can we use the disk directly within LINSTOR? Is it possible?
Well, we have some helper functions in LINSTOR that when we get a full disk, that LINSTOR will create the volume group on it for you.
Okay.
So like our Kubernetes integration with the operator uses that. So,
okay, so it's required.
Yeah.
Anyways, okay.
In a way, it's required, but it's not required that you do it. Right?
Okay.
Okay. Yeah, so here on this slide, I have a full example of what could be in such a resource group, right? So again, this with the tags on the nodes, and then you can express a policy like, I want to have all volumes in this resource group should be three-way redundant, where two of the copies are in the same rack, but in different in the same rack, right?
Yeah.
Yeah, or it could be, different chassis, but same rack and so on. So you really, this is your freedom. Here you define what it does.
So you can have failure domains even in your racks and data center. And,
yeah. So this is where we define what is a failure domain. What kind of failures can you mask with it?
Yeah, that's great.
And similar, the same mechanism can be used to select the path over the network in case your network allows for multiple paths. Yeah. But let's see what else I have here on slides. Right. So let's switch gears and look at the upper layers. So what connectors do we have available? So you can connect LINSTOR to Kubernetes. And for Kubernetes, we have the full range of things. So it's the CSI driver, the operator, the stock scheduler. Well, I learned recently that this is like going to be deprecated soon because there is now some functionality in Kubernetes or CSI driver that replaces that. And what it is about is that we deliver feedback from LINSTOR to Kubernetes telling it, okay, listen, Kubernetes, if you place the container here, you get better storage access than when you place it on some other node. YAMLs and the operator is in the Red Hat type framework and also available in the Ubuntu Jumped framework. And yeah, the kubectl plugin, that's very convenient for Kubernetes admins because you get all the LINSTOR commands at your fingertips in the kubectl command. Then the Nomad CSI driver, I need to remove that. It is verified. It works with Nomad as well. We have the driver for OpenStack since April 2019, upstream in the OpenStack project. We have the OpenNebula driver, which really keeps or is released on the same pace as the OpenNebula releases as well. So we really track how OpenNebula moves forward. A Proxmox driver, XCP-ng, and the Apache Cloud Stack driver, and that is interesting. This is going to be released like any day now with the Apache Cloud Stack collaboration conference going on right now in parallel.
I guess today, like after 6 p.m.
Yeah.
Something like that.
So really hot news. Yeah, here's some background on our Kubernetes work. All the Kubernetes work we do under the brand name Piraeus Data Store. So that contains all these components, and you find it in the Piraeus Data Store organization on GitHub. And this project formally joined the CNCF and is a sandbox project of the CNCF, right? That's the correct wording. And yeah, so maybe to explain a little bit about our business model. So on the Piraeus Data Store, we have everything available. Well, from the source code and then also the pre-packaged containers are on Docker Hub, Quay, and like the equivalent in our enterprise product is then is also there, and always with little differences. So for example, the container base image is Red Hat UBI, and with that it can be certified for Red Hat OpenShift. And in order to run on Red Hat OpenShift, it comes with precompiled DRBD drivers for the Red Hat kernels. So here are those little differences in packaging, but in the end, it all builds from the same source code. It's open source software, just a little bit easier for the enterprise user.
And also includes definitely an enterprise support.
Oh, of course, there's support 24/7 by the teams out of our 2 offices in Vienna and United States. Yeah, and I'm coming to like the last slides of my presentation. So here I have this translation matrix cheat sheet. So what I call a resource group in LINSTOR is a storage class in Kubernetes, a data store in OpenNebula, a volume type in OpenStack, a storage pool in Proxmox, a storage repository, and a primary storage in CloudStack.
Yeah, it's
with the volume. Sorry.
It's all different, different namings.
Yes, and in the meantime, I learned that Nomad uses the same expressions as Kubernetes.
Okay.
With volume, it's not so difficult. It's nearly everywhere called volume, with the exception of OpenNebula, they call it image.
Yeah. That was my confusion in OpenNebula, yes.
But naming is hard, as we know.
Naming is hard.
So we need a translation sheet. Yeah, so to sum it up, LINSTOR can help from discovering the hardware, does the node level volume management, adds some features on top of it, and brings it to the orchestrator of your choice. Okay.
Thank you, Philip, for this detailed explanation of LINSTOR and DRBD and the Linux components. And I don't know how many times I listened these things from you, but I never get bored. It's always interesting. And now I have a couple of questions that you might be found interesting. And the first question is from Pavel, and he's asking, I already know the answers, but I will ask you anyways. So he's asking, is there an official GUI planned and when it will be released?
Yes, there is an official GUI, and it is part of Linbit SDS, so part of the commercial offering. It is already available to our customers, and it is actually going through its second round pretty soon. So it will get a major overhaul within weeks.
Okay. So all the subscribed customers can reach and found this, can install this GUI from us, right? It's not open sourcely released.
Yes, it's part of the commercial product, and recently we added some documentation in the user's guide, so you will find a few hints how to install it and how to use it.
Okay, thank you. Another question is related with LINSTOR again, and it's from Dimitri. And Dimitri asks, why was the Java chosen for LINSTOR? Among the more popular languages in the community, example for Golang, and he's thinking that the big problem of the Java, because it slows down the work for the community a lot, and the amount of people from the community able to contribute would be larger if a more popular language were chosen. Now Golang is becoming almost a standard for developing infrastructure things. And why did you choose Java over Golang?
You know, when I search the internet for language popularity, or you find different indexes like Tiobe and other ones, and at any of those rankings, Java is way more up than Golang. And that was also the practical consideration when we decided it, is that, you know, I have multiple developers on payroll that are capable of writing Java. And at that time, I had one guy who was learning Golang. And when I look at the candidates I get for my team, you know, they learn Java at the university, but no one has Golang courses at university. So from a practical point of view, Java is much more widespread. It is long around. The library ecosystem is in a much better shape, in my perception. Sure, you know, we use different languages for different components. For example, we have components in Golang, like all of our Kubernetes integration. I think also DRBD top is also implemented in Golang. We have components. Yeah, DRBD Reactor is written in Rust.
In Rust, so, okay. I remember maybe it was Go, but okay.
No, that one is written in Rust. So of course my developers are also interested in trying out new stuff.
Okay.
But I need to add, we're pretty happy with having Java as the language for LINSTOR itself, because LINSTOR is a pretty big code base. Mm-hmm. And it turned out to be a good tool for the job.
Okay. Thank you. And another question. Is there any plans to increase amount of floating peers for DRBD? Now maximum 2 are available. I guess he's referring pacemaker floating peers.
Mm-hmm. Okay. That's an interesting question. Yeah. But I think there is more than 2 possible. But well, I have to look it up myself.
I am now checking our user guide. Maybe we somehow defined it.
Yeah, but the floating peer thing, that's just the way how the nodes are identified. So it would surprise me if it's limited to 2, but I need to check myself.
Okay.
But Yusuf, there is another question I see here in the chat of the session. I will read it from Victor. What kind of monitoring comes with Linbit? And let me answer right away. So we now support Prometheus and Grafana. So both components, LINSTOR and DRBD, can export or provide all the metrics for Prometheus. And we have a Grafana sample dashboard on this Grafana hub, I think it's called.
Yeah, it's a Grafana.
So that's the way to go, Prometheus and Grafana. We support that.
Okay. I don't have any questions here. Do you see any other in the chat? Let me check.
I think we forgot this one. Does snap and clone of golden image of OS for all VMs use LINSTOR can be created? Okay, I think I get the question. I will phrase the question in my words. So in a infrastructure as a service cloud, when there are like template images for VMs, can those be snapshotted for the customers, or are they going to be cloned for the customers when a customer instantiates one of those templates? And the answer is,
I think I understand too. Okay, now I understand. So it's like a one image for all VMs, and then you can just clone and use. Okay.
Yeah. And the answer is we support both, but scalable is that you do a clone. And then the clone, how the clone is done depends a lot on the backing technology. So for example, we support very efficient cloning on CFS, and there the cloning is done with CFS send and receive. And yeah, and but it's both is supported. So doing snapshots, and there, I don't know all the details from top of my head. You need to have a LINSTOR expert, right?
Yeah, we have better LINSTOR experts in our team, right? While you just said about snapshots, and let me ask you one question. It's not from any other, it's from me. So how about having a disaster recovery in LINSTOR? How do we do that?
Right. Yusuf, thanks for the question. Yes, so what we added very recently is that LINSTOR can do snapshot shipping between LINSTOR clusters, so between independent LINSTOR clusters. So let's say a marketing term for this would be it does federation. So you
it's
have
a federation in Kubernetes, right?
Yeah. So you have LINSTOR clusters that have their own controller, they're independent. But then you mark one of those volumes in one cluster and say, okay, I want that to be regularly shipped to the other cluster. So, and regularly like every 5 minutes or every 10 minutes. And then it only sends the difference in between. So it does snapshots, creates the difference, the deltas between the snapshots, and then it transfers this snapshot delta to the other cluster and applies it to the other volume. So you have there a DR site where you have the same volume, let's say on a granularity of 5 minutes or 10 minutes for disaster recovery purposes. And this kind of replication is really independent of the network bandwidth. So it is very robust for these DR scenarios.
And this snapshot shipping can also be used for backups, right? You can also send your volumes into S3 targets and such.
Yes, that's also a very recent feature.
Yeah.
Okay.
I think we are done. The questions are stopped, so that means we can also stop.
And we also filled our time slot like
yes.
on to the minute, right?
Yes, it's a surprise. So after half an hour, I have another session if anyone is interested with one of the LINSTOR engineers, Renee Painter, and we will try to show you guys how to use LINSTOR with OpenNebula. It will be a demo that we will do together, and you can see how actually what we are talking about here is actually working in real life. It's a demo setup, so don't expect too much, but it is something that you can see within your own eyes. Okay, thank you everyone for joining this session and listening to me and Philip and interest in our solutions. And hopefully we will see you again in 30 minutes. Goodbye.
Goodbye.